All right. So in the previous class, I taught about R2 and adjusted R2. Along with that, I explained the hyperparameters in linear regression, and I have also shown you a basic implementation code of linear regression. Okay. So in linear regression, we are assuming that as per the equation, the relationship between dependent and independent variable is linear in nature. We calculated coefficients value for simple linear regression, beta naught and beta 1, by optimizing cost function. Then I taught about the evaluation criteria for regression, in which I talked about MSE, MAE, RMSE, R2, adjusted R2. The main criteria is MSC. We do calculate the root of MSC also, that is called as root mean square error. Okay. However, if the errors are more, then we select MAE to show that this is our criteria for evaluating a model. Because MSC is more, then we can't represent a model with that error value. So it's better to calculate the absolute value. So MAE is preferred. These are related to the errors, and in the previous lecture, I explained about the two, R square and adjusted R square. They explain variance. They explain variance. That means how much independent features are contributing in predicting the value of y. It lies between 0 to 1 if I do talk about R2. But there are some issues in R2. It doesn't tell us about the number of features, it just only tells about that how much contribution has been given. For that, we have changed the term from R2, we made a new formula, adjusted R2, where we introduce the number of features also and number of samples also. How many rows are there? So number of columns and number of rows also we mentioned. So it will give you an idea about how many features are there. By keeping this much features, this will be the R2 value. By keeping this much features, this will be the R2 value. Okay, because R2 may be subject to overfitting. Why? Because let's suppose we do have 0.35 value of R2. Initially, we are having 5 features over which 0.35 value we have achieved. By increasing the number of feature, it may happen that your R2 will increase. So if you become happy that okay, more variance is explained, we are having a good model, but that's not the fact. We never we never keep R2 on priority for a model evaluation. We don't do that. MSC is the major criteria. Error calculation is the R2 is not the major criteria. Though yes, we calculate R2. R2 is dependent upon your data also, data to data, it will change. Okay, so there are many factors that will change the R2 score. So we are not strict to. Fine. Instead of R2, if we are having an overfitting model, we prefer adjusted R2 so that here if I say na, I added one more feature, my R2 score become zero point 0.4. It may happen that this feature may be correlated with any of the feature which are present here. Due to that reason, R2 is increased. So that is violating my criteria, my assumption of linear regression. So by having a solution for this particular problem, we use adjusted R2. Adjusted R2 is also like regularization. That means it will penalize. Okay, it will penalize, penalty for adding extra features in your model for prediction. It will penalize adjusted R2. Okay, so these are the evaluation criteria. Yesterday we have also seen how to use linear regression model. It's like, okay, you have to take the linear regression model from linear model, and just you have to use it by putting the value inside it, fit model dot fit, and you will get the predictions. Okay, but okay, that's the general case for linear regression. However, in real world, it's not mandatory that you are always going to find a linear relationship between the feature. It's not mandatory. Right now you are assuming that, okay, this is my data, I am having certain features in the data, and they are linearly related to y, they are satisfying this equation. Okay, but it is not mandatory. It may happen that polynomial relationship can also be there. Okay, polynomial relationship. How? You may have an equation like this: y equal to beta naught plus beta 1 x1 plus beta 2 x2 square plus beta 3 x3 cube. It may have a possibility for having such kind of relationship also. And if you fit such data into your linear regression model, definitely you will fail. If there is a polynomial relationship between x and y, and if you are using linear regression, you will fail. Okay, your linear regression evaluation criteria will give you huge MSE. So there are many ways, okay, how to approach and how to understand what's happening with my model, what's happening with my results, how to approach. That's why I do the projects, and I call the people that see how you are processing the data, what are the steps you are following over the data. I already told you that linear regression requirement is all the assumptions which we have listed previously. If you have done all the assumptions over the data, and if you put this data into linear regression model, then it should give it should give best results. But even doing these things also, you are not getting best results. So there are three options available to us. According to my analysis, three options available to us. These three options are: either you again check your data analysis, recheck data analysis whether you did any mistake or everything is correct or not. Recheck your data, entire analysis, recheck. Second is change your model. Okay, linear regression not giving good results. Okay, change model, use any other model. Third one is, okay, it may happen that if linear is not giving the result, there might be a polynomial relationship. These three options you have to apply. Okay, so what is this polynomial regression? Let me share my entire screen, as I already gave you the equation for polynomial, and it's quite clear the relationship which independent and dependent have for the polynomial. Okay, so polynomial regression. Polynomial regression is also a form of linear regression only, but polynomial regression is a form of linear only. If the people thinks that, okay, we are having any other algorithm or separate algorithm for that, no, that's not the case. Polynomial regression is a form of linear regression only, where we do model our, okay, we perform modeling according to nth degree polynomial. That means we try to fit the data, not considering that it is having linear relationship with the target. We fit it by considering that it has non-linear relationship with the target. That's what we do. So while model training, we will specify poly. We'll see code ahead, don't worry. We'll specify poly. Okay, so there are some relationships in the data which are not specifically linear, which may be polynomial. If we try to fit linear model to curved data, we will get a scatter plot of residuals on the predictor, will have patches of many positive residuals in the middle. That means it's trying to show you that how your visualization looks like if you are trying to fit a linear model to curved data. Okay, linear model to curved data. Okay, you may have some different plot. You are expecting a line, but that will be not a line. That will be some curve linear, something like that. Okay, so an assumption in a usual multiple linear regression is that all independent are independent. all independent variables are independent. That means they are not related among each other, and they are related to the target with a with a linear relationship. But here it is saying that in polynomial regression this assumption is not satisfied. So how does it works? How does polynomial regression works? If we observe closely, that we will realize that to evolve from linear regression to polynomial, we have to just suppose to add higher ordered terms in the dependent features in a feature space. This is called as feature engineering, but not exactly. Again, what actually it is talking about? Feature engineering and all this, and they are certainly confusing to us. The next are just only the applications. Okay, just only the applications, and they are specifying in this particular way. Application for polynomial regression. Okay, the growth rate of tissues, the things are not non-linear always. Disease epidemics, or I would say LLMs research. Okay, that is exponential, that is not linear. So these are the applications. Okay, so what exactly is happening here in this? You can see, for example, this is your equation. I believe that this is a linear equation. Why? A plus b1x, the degree of x is 1. B2 square and e, these are the constants. No? So degree of constants doesn't matter for the equation. If I write like this, y equal to mx plus c, and if I write y equal to mx plus c square, still it is degree 1, because the power of x is 1, so it is linear. This is also linear, this is also linear. Both are linear equations. Okay, so I guess here also x is having 1, so it's linear. Now in this particular case, here x is having higher degrees. So because it is having higher degrees, this is a polynomial. Okay, it shows the polynomial relationship. If I draw a plot, now again, if I draw a plot between x and y, this is x, this is y, it will certainly look like this polynomial relationship rather than a linear. Okay, rather than a linear, it is showing such kind of curve. And we do name it like, here it's mentioned that in real world not all the data is linear, we may have non-linear data also. So we have to fit a non-linear model for that. That is called as curve linear. So it will be not linear regression, it will be curve linear regression. If you are using polynomial, then it will be curve linear regression, not linear, so that it should better fit. Okay, better fit your model. Fine. Let me check some more details as I'm looking forward for in my notes section. Okay, I have shared this thing. Okay, linear regression. If I just check the notes. Okay, let's talk about the summary. Okay, so these are all available with you. I have shared. Okay, anything here? Okay, MSc, RMSc, MAE, R2, everything I told, including the parameters also, features also, everything I told. All right, so nothing more available to me at this particular time related to your polynomial. Only a brief introduction about what is a polynomial relationship. What is a polynomial or curve linear regression? Okay, fine. I will put up this topic again by a code and by few more example at this particular time. Just we have to understand the relationship between y and x is not linear in nature. We are having some higher degree terms. Okay, and the one which it introduced as a feature engineering, I hope it created an chaos for you. Feature engineering. You know what happens? What is feature engineering? Creating new features from existing. That is called as feature engineering. So in your data, it may be like you are having certain features x1, x2, x3, x4. This is your y. For example, you are creating a new feature x5 that will be the multiplication of x1 and x2. The creation of new feature is called as feature engineering, and this new feature is a product of x1 and x2. Since it is a product of an x1 and x2, it may happen that now the degree which is present in x5 is of degree 2. And if I take this x5 into my analysis for regression, obviously it follows polynomial, not linear. That's what it was saying. Okay, so either I did feature engineering, I got some higher order term. Either if I haven't done any feature engineering, but still there are higher order terms present in my data. So for that purpose, I need to use curve linear, or it will be like polynomial regression. Then only I can fit the points over these, because the points will be fitted on the curve, not the line. The curve linear will be like this also. So I need to fit the points over the curve, not the line. Here I need to fit the points, or either above or below this curve. Okay, there is no line. If I do look out for the line will be like this. So the distance of the points which you are expecting on the line, and which is but it should be like on the curve, the error will be huge. And because the error is more, obviously your model will fail. So if you are getting more errors, high errors, let's try for polynomial. This I will show you in the coding part. Okay, and then I will explore more. Just I give you brief or introduction related to it. Okay, so whatever we have seen so far is linear regression is a good algorithm, widely used algorithm. The application is very much for linear regression. Okay, so talking about advantages and disadvantages of linear regression, we can we can talk from the summary of linear regression. Okay, so if it's been there, let me talk about this thing. All right, I guess I have to refer to any other notes for this to talk about advantage and disadvantage. Okay, now let's take from linear regression. What is linear regression? Fine. So the advantage of linear regression is it is interpretable. Okay, we can calculate the coefficients value, beta naught, beta 1. Okay, not so much high level or high or complex solution we require. We can easily interpret the value of coefficients. So it's interpretable. Linear regression is simple algorithm, not complex computational algorithm. It's a very simple algorithm. You very well know that this is only the equation we are following up, so we don't have to stress a lot. So it's simple. Efficiency is good for linear regression. It is suitable for real time applications. And what I know is in the industry, linear regression has been widely used for uh, the organizations which look out for sales. So, sales prediction, there they use linear regression is one of the widely used algorithms. Sales prediction. Okay, linear regression allow easy testing. Okay, assumptions are pretty much clear, linear relationship, normal distribution, constant variance, that is this term, independence of errors, and all these things you very well know. Okay, linear regression provides information about importance of feature through the magnitude of the coefficients. Okay, that also it do. That we'll talk more about it in this upcoming topics. So coefficients beta 1, beta 2, beta 3, they tells how much powerful x1, x2, x3 are. They tells. Okay, the power of coefficient will tell you how the features are important for us. Okay, because these features are multiplied by the coefficients only. If the coefficient value is very less, then if I multiply feature with such coefficient, its value will be very, very less. So the importance of this feature will be down. But if the value of coefficient is more, then feature will be important because the result will be more. Okay, so in that regards, it is saying, okay, these are the advantages. Disadvantages are, okay, we have to initially assume that the features are linearly dependent. Yeah, assumption hai. This is what we have to be, if you are starting linear regression algorithm, this is what you have to assume, that the relationship between features are linear. Okay, prior assumption. Outliers, they may impact every algorithm. Okay, outlier impact every algorithm. So if you can remove the outliers and then if you apply the linear regression model, then it is fine. So remove outliers from the data. Huh. Linear regression model may be subject to overfitting and underfitting. It is also less flexible. Okay, because of linear relationship assumption. So what these two means? There you may have a multicollinearity also, that I told that it's an assumption that there should not be any no multicollinearity, but there may be a multicollinearity where two or more independent features are highly correlated. They will give a rise to multicollinearity. We don't want features to be correlated. They should not, their points should not come in a straight line one by one. No, we don't want that thing. Their point should not come like in this order. In that particular case, my model will overfit because instead of learning, it will memorize. So what it is saying? Okay, what it is saying exactly? It is saying that the disadvantages. Okay, the disadvantages. I want to the last two to three. I want to explore. It told that linear regression can be overfitted, it can be underfitted. Okay, overfitted and underfitted both. Overfitting, I told that we are having we are having high score on training, but low score on testing. That is what we called as overfitted. In underfitting, we are having low score in both training and the testing. So That means model is not at all capturing the relationship or patterns in the data. Overfitting the case will be like if we are giving correlated features, collinear features in our data for training. This is the reason for overfitting. Okay, that's the main reason. Main reason for overfitting. Correlated collinear. Okay, that means if the features are in correspondence, so if my model captures x1, definitely it will capture x2 also if they both are correlated. So linear regression model, if you are going to train it with so many features, it will be overfitting. There is a chance of overfitting. Okay, and in case of underfitting, either you haven't done your data pre-processing proper according to the requirement of linear regression, either there is a polynomial relationship, that is why you are getting low score, high error. These may be the two issues. Either your data not at all fit, your x is not at all giving the prediction for y. These may be the reasons for overfitting and underfitting in a linear regression. So correlation, collinearity, everything I covered here. Okay, being as a data scientist, we have to check out for all these interpretations. What is happening with the data? What next we can do? What is the possibility? Okay, how much data is available? Data is something which is the first and the foremost priority for you to analyze. This is the one thing. Then the model comes the next. So, because of this overfitting of linear regression, the issue of overfitting in linear regression, we have to look out for different techniques which are associated with linear regression, but do we have any other possibility so that we can reduce the overfitting in the model? Yes, we have. In linear model, we pick linear regression from linear model. In linear model only, we do have less so rich and elastic net. These three these three algorithms too, which are associated with linear only, like linear only, but they introduce penalty for getting overfitted. Penalty. They penalize. How? Where to give the penalty? We have to give the penalty into that equation from where we have started the derivation for linear regression. You started the derivation of linear regression from here, cost function equal to summation of yp minus y ka whole square by n. This was your cost function. You have done the derivation from this cost function only for linear regression. Okay, from here only you did started. We will be adding penalty in this equation only. Here only we'll add penalty. Less so is called as L1, ridge is called as L2, elastic net is L1 plus L2. It's a combination of both L1 plus L2. So, what exactly the penalty is? See, if your model is having correlated collinear feature, because they are the responsible person for co collinear correlation to have overfitting. So penalty will be, we have to reduce the impact of such features in the data. That's what you have to do. Those features which are performing this kind of activity, collinear correlation, we have to reduce the impact of them. How? If we check out this equation, y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, that is for multiple linear regression. For example, x2 and x3 are correlated. Okay, these two features are correlated. Now, because of their correlation, my model is overfitted. I need to take care of that. So, what I will do is, see with x1, x2, or x3, these are the features already. These are the existing features which are fitting in the equation. I can't do anything with that. The thing which I can do is with the coefficients. Because x1, x2, these are already existing. These are existing in my equations. I fitted these things into my equation. So if I want to penalize, the approach will I will use is to treat the coefficients. For example, since x2 and x3 are correlated, if I make the value of beta 2 0, so 0 multiplied by x2 will be 0, and x2 will be dropped, x3 will survive. So whatever I can do here is I can apply something, some technique, so that I can adjust the value of coefficient. With this only, I can remove the overfitting in the model. Okay, for that purpose only, we are having Lasso and Ridge. These two regression algorithms, very popular. They are part of linear regression only. Both are used to prevent overfitting in the linear regression model. Okay, errors means error वो टेस्ट वाला, ट्रेनिंग वाला नहीं. ट्रेनिंग में तो इन ट्रेनिंग माय लीनियर रिग्रेशन मॉडल विल से आई एम द बेस्ट, but actually the more error appeared in testing. So these words are related to reduce the error. That means they are talking about test data, how to reduce the error. We will say that to prevent overfitting in the model. They are also called as regularization techniques. Regularization techniques. Okay. Now, let me have some more talk. Regularization. Now, it is very much important. Not very much. Very, 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 as much as very you can put. Regularization, normalization, standardization, very much important. All these things. Because we do apply this pre processing over the data, then only our model success. Else, model will say you tata bye bye. Okay. These techniques are very effective techniques. Either you are machine learning, deep learning, generative AI, everywhere applicable. Okay, I want to just show you some like example. Let us suppose this is the axis, and this is okay. These are the 2 points A, B. This is O origin. So if I ask you how I will reach from A to B, how I should reach from A to B, you will say, sir, there are two ways to reach from A to B. Either you can go from A to O, and then you can go from O to B. So AO plus OB. So you can reach from A to B. Such kind of approach is called as Manhattan. It's called as Manhattan distance. One more thing is you can calculate the shortest distance. You can come directly. Where you will take under root of OA square plus OB square. That is your AB. It's called as Euclidean. Okay, it's Euclidean distance. I hope you got it. And why I'm telling this thing, because I'm going to use these two in my L1 and L2. Okay, I'll talk more about these. I hope this makes a sense. You did understood the concepts. Okay, let me stop recording.